One thing that will help you gain a full understanding of the conservation of energy with or without non-conservative forces is to remind yourself that joules are always conserved. So that's true for conservative and non-conservative forces. So let's look at two examples. Let's look at an example of conservative forces versus an example with non-conservative forces. So with conservative forces, we're only talking about gravitational potential energy, kinetic energy, and spring potential energy. There's no work done by non-conservative forces. So the sum of the energy before is going to be equal to the sum of the energy after. So let's just say that initially we have a total of 40 joules of energy, so that means we have to maintain those 40 joules of energy. They can't disappear. Joules don't disappear. So if we expand this as an example, let's say our example has both gravitational kinetic initially, and later we still have gravitational and kinetic. So what happens to these 40 joules? Well, let's say for sake of example, initially we have 17 joules of gravitational and 23 joules of kinetic. 17 plus 23 is the 40. And then after something happens, the object moves, and we have 5 joules of gravitational and 35 joules of kinetic. And you see that we still have 40. All that happens, it looks like gravitational potential energy lowered and kinetic energy was raised. And we can further interpret this a little beyond the scope of what I want to show here, but I'll take the opportunity. Since we see that the kinetic energy has increased, that tells us that the object must be moving faster. And since the gravitational potential energy decreased, that must mean it went from a high height to a lower height. Now let's look at a case in which we have non-conservative forces present. So something like friction or air resistance is acting on the object as it is moving. So our initial energy, I'll still use the 40 so you can compare the two. So initially we have 40 joules of energy, but what happens as the object moves, we have 10 joules of work done by friction or air resistance acting on the object. So we write that on the left side as a negative. So what that means is at the end of the problem, when everything's done, the object has moved, what are we left with? Well, we're left with only 30 joules. And the reason is because 10 of those joules, 10 of the original 40, got used up by a non-conservative force. So what does that look like? Well, let's say that we have GPE, we have KE, we have the non-conservative work being done by the non-conservative force, like friction. And at the end of the problem, we have GPE and KE, like we had before. Okay, we're starting off with 40 joules total mechanical energy. So 17, like we had before, and 23, like we had before. But we have friction present, and friction is stealing some of those joules. We know where they are. We're never going to get them back, though, but we know where they are. So 17 plus 23 minus 10 is going to be equal to 30. So on the right side, we still have to have 30. So what happens? Well, we went from this height, which gave us 17 joules, to this height, that height, which gave us 5 joules, which means that we only have 25 joules of energy left over for kinetic, which means that this object here, or this scenario, that object is moving slower than in this scenario. And that's because some of the energy was given up, never to be retrieved again. It was given up to friction. So although the sum of EI, 40, is the same in both cases, the final kinetic energy is only 25 due to the non-conservative work being done on the object.